So student, now we are going to discuss this question number 7.22, clear? And in this question it is given to you, in this question it is given to you, we have some part from A, B, C, D and E, clear? And we have to answer the following questions, clear? So concentrate. If we talk about first part number A, in this part it is given to you, in any AC circuit, is the applied instantaneous voltage equal to algebraic sum of instantaneous voltage across the series element of this circuit, clear? So is the same true for RMS voltage. Now concentrate. Let's suppose we have, this is inductor, let's suppose we have capacitor, and I can say this is resistor, and all are connected with an AC source like this, clear? I can say this is V, and we can say this is corresponding to L, this is C, and this one is R, clear? So I can say, let's suppose I am saying this is V naught sine of omega t, this voltage is varying in nature, clear to you? So now we can say in any AC circuit, we have this AC circuit, so is the applied instantaneous voltage equal to algebraic sum of instantaneous voltage across the series element of the circuit. So definitely you can see, whenever we are talking about instantaneous voltage, so instantaneous voltage definitely it will be distributed in L, C and R, clear? And at the particular time, the value of V, it should be equal to sum of this one and this one, means sum of potential across L, potential across C and potential across R, clear? So definitely I can say this statement is correct. But is the same true for RMS voltage? No, clear? You cannot write like this, Vrms is equal to RMS voltage across L, RMS voltage across C and RMS voltage across R, and we are doing the addition, clear? You cannot write like this. Why? Because there is a we can say there is an opposite phase between capacitor and inductor voltage, clear? So at the time actually you have to find resultant voltage, clear? And at the time you can say R and the resultant of VL and VC, they are perpendicular to each other, so directly you cannot say that V equal to VL plus VC plus VR, clear? So we cannot say for RMS voltage. Yes, for instantaneous voltage this statement is correct, clear? Now if I am going to discuss part number B, a capacitor is used in the primary circuit of an induction coil. Yes, why? Let's suppose if I am saying to you situation, a primary coil breaks, clear? A primary coil breaks, at that time you can say initially let's suppose a steady current is flowing in that primary coil, and finally it comes to zero after a certain interval of time. It means value of current decreases. When value of current decreases, it means definitely induced EMF will be generated, because there is a change in the flux is to be taking place. Yes or no? So induced EMF will be generated, and if we connect a capacitor with the primary circuit of induction coil, at that time due to that induced EMF, that capacitor is charged, and we can say instantaneous sparking that takes place due to breaking of that coil, that is prevented, clear? That's why we are using capacitor in the primary circuit of induction coil, clear? Now we are going to discuss part number C. In this part number C, it is given an applied voltage signal consists of a superposition of DC voltage and AC voltage of high frequency, okay? The circuit contains an inductor and a capacitor in series, show that the DC signal will appear across C and AC signal across we can say that is L. Now let us try to understand. Let's suppose we have this is L, and let's suppose this is capacitor, both are connected in a series. We have here this is voltage source, clear? Initially I am taking this voltage source is to be AC voltage source, so I am saying this is Vrms. Initially we have AC voltage source, so at the time I can say voltage that is produced across this inductor, and voltage this is produced across this capacitor, this is VC, clear? So I can write like this, value of VL, this is given by I times of XL, clear? And we can say it is given by I times of omega L, clear? Omega L. Now you can also write like this, I, we can say this is 2 pi f L. Now listen very carefully. Whenever we are talking about AC current, so for AC current we have a definite frequency, clear? It means definitely we will find some value of voltage across this inductor. So this is value 2 pi FL, clear. But if I am talking about this capacitor, clear. If we are talking about capacitor, we can say this is given by I times of Xc, clear. Xc is given by, this is 1 by omega c, clear. I can say I, this is equal to 1 upon 2 pi Fc, yes or no. So from here you can say, if we have a certain value of Bc, definitely we are getting here voltage across capacitor also, clear. So what is this question? Question is given, an applied voltage signal consists of a superposition of a DC voltage and AC voltage. Okay, then circuit consists of an inductor and capacitor. What will happen? Listen carefully. Now you can say this source it actually consists of DC plus AC. Now we talk about AC, clear. In AC we can say all the potential difference you will find that is across the L as well as across C, clear. But what about DC current? Clear. What about DC current? In DC current you can say we have frequency 0. So whenever we have frequency 0, the resistance that is offered by inductor, we can say this is equal to 0. Yes or no? I can say this is 0, and we can say resistance, this is offered by capacitor, this is infinite, because value of frequency we have 0, clear. So from here you can say this is infinity. It means I can say all the potential difference in the case of DC you always find across this capacitor only, clear, and there is no potential drop across this inductor. That's why you can see in current electricity chapter, if you are connecting this coil into circuit, there is no effect in the resistance or there is no effect in the heating. Why? Because I can say the resistance offered by this coil, by this inductor with respect to DC current, that is 0. Yes or no? So I can say there is no use. You can assume it just like a single wire, or a wire that is having 0 resistance, clear. So I can say in the case of DC, all the potential drop you will find across this capacitor. But what about AC? In the case of AC, you will find some potential difference across this VL and some potential difference across this VC, clear. And what is net potential? It depends on the magnitude of VL and VC, clear. So this is all about part number C. Yes. Now, if we talk about part number D, in part number D it is given to you a choke coil in series. A choke coil in series with a lamp is connected to a DC line. Okay. So a choke coil is connected in series with a lamp in DC line. Okay. The lamp is seen to be shine brightly. Fine. Insertion of an iron core in the choke causes no change in the lamp. Yes, because if we are talking about DC current, for the DC current resistance offered by choke coil is 0. So at that time, if you have a choke coil, you are inserting any we can say iron core, that causes there is no change in the brightness of a lamp. But what will happen when we are talking about there is an input of an AC line, AC current? So whenever we have input of AC current, now choke coil will definitely it will oppose, it will actually exert some, it will actually develop some impedance or resistance across the path. And whenever we are placing this iron core inside this choke coil, definitely the impedance that is offered by this circuit, it will be more. It means I can say overall heat loss will be more, and you will find this lamp is to be seen brightly but with a dim light, clear. It means I can say intensity of this light decreases, clear. So this will happen with part number D, clear. Now if we are going to discuss part number E, why is choke coil needed in the use of fluorescent tube with AC mains? Why can we not use an ordinary resistor instead of choke coil? Now listen carefully. Actually, whenever we have supply AC mains, at that time VRMS that is coming to us, this is 220 volt, clear. Let's suppose we do not have choke coil, we have only resistor. At that time this potential difference is very large, and at that time I can say and instantaneously a large current will flow through this fluorescent tube, and this due to this large current we can say this fluorescent tube, it may be broken or it may be damaged, clear. But let's suppose if we are connecting this choke coil, clear. So at the time some impedance is actually across this choke coil we will find, and there is some current is to be flowing there is some current is to be flowing in a fluorescent tube, clear. So that's why we can see we are using choke coil instead of we are choke coil with the AC supply, clear. But if we have a DC supply, yes or no, whenever we are using choke coil, clear, we are not using ordinary resistor. Why? Because in the ordinary resistor, if you connect it, you will find that a large amount of heat is generated, because P equal to I square R, clear. I square RT is the amount of heat generated. So large amount of heat generated, when large amount of heat generated, at the time definitely the circuit may be burnt, clear, or we can say this fluorescent tube, it may be damaged, clear. So this is all about this question number E, clear. So this is all about total questions.